Hi, and welcome back to Troubleshooting Python Machine Learning. Today we're starting a new section on wrangling with unsupervised learning and a curse of dimensionality. In particular, in this section, we're going to take a look at clustering methods or any unsupervised learning methods where there isn't a target per se, but we're performing machine learning to find different clusters or similar things within our data sets. Sometimes, or most often, to then feed this information down or analysis downstream to a supervised learning model. Let's look at the four things we're going to look at. So number one, we're going to take a look at labeling the dimensions with original feature names after doing PCA. Number two, we're going to take a look at clustering text documents with Scikit-learn k-means. Number three, we're going to take a look at listing word frequencies in a corpus using Scikit-learn functions. And number four, we're going to take a look at the pipelines feature in Scikit-learn, and we'll use it to do polynomial kernel regression. In this video, our topic is labeling dimensions with original feature names after performing PCA. So PCA is a very popular technique for unsupervised clustering and dimensionality reduction. PCA stands for Principal Components Analysis. The idea is after performing PCA, you're returned a linear combination of features which then form dimensions that explain the most amount of variance from 1 to n. So we're going to take a look at, in this video, how we can apply PCA on the iris dataset. We're going to then take a look at how we can understand the output of PCA and what it does. And lastly, we're going to get the meat of the solution by extracting the factors that contribute to each principal component. Let's go in and take a look. We're back in Jupyter Notebook, and as usual, we're going to import the usual suspects of our data science pipeline. We'll have pandas, we'll have NumPy, and we'll have all the Scikit-learn guys. Next thing we're going to do is to load up the iris datasets. As usual, you can see that we're just using the datasets package in Scikit-learn, and we're going to transform the data into a data frame using the features name as columns. We're going to take a look at what this looks like. It's nice and simple. The thing that we always need to remember is there are many classes of algorithms and models within the machine learning world, which requires us to standardize our data. And by standardizing our data, it means we'll take the data, we'll compute its mean, it will subtract the mean from all the data points, and we'll also divide all the data points by its standard variation. What that gives us is, it means that the whole variable is now centered around 0 because we've subtracted the average, and it has a variance of 1 because we've divided by the standard deviation. What that gives us is, if you have two variables that describe the same data point but in much different magnitudes, for example, if you have height versus weight, and your weight is in stone and your height is in cm, obviously if you're explaining the variance, then the height being a number that's usually between 120 to, let's say, 220, that would be a much bigger number, thus it would look like that explains the variance a lot more. So here in PCA, we always have to remember that we need to normalize the data. So there are multiple ways to do this, but the easiest way is to just simply say we'll subtract the mean, and then we'll divide it by the standard deviation. Let's fit a very simple PCA algorithm to this. I'm sure you guys all know how to do this. So maybe 4 components, and we're simply going to apply this to the normalized data frame. There we go. The first thing we're going to take a look at is, amongst the 4 components, how did we explain the variance in the data sets between the four components. So the first thing that we can use is the explained variance ratio property of the PCA model after we've fitted. So you can see that the first component explains 72.7% of the variance, and then 23%, and then 3%, and then less than 1%. So a common thing for us to do is to kind of find a threshold, maybe here, where we say, okay, 3 components is enough, and then we use the new dimensions to then perform downstream machine learning. So how do we go from understanding how the components behave and how much variance they explain to actually finding out and labeling the components themselves? So the first thing we need to do is to create an identity matrix that is shaped like data frame. Like that. The next thing we need to do is to transform this matrix using the PCA model that has learned how to do the dimensionality transform on our data, and then create a new matrix that has our components. The reason why we're using a diagonal matrix is because we can then extract each component of each data frame correctly. There we go. And actually that's all there is to it. What we needed to do was to create an identity or matrix with a diagonal being 1, identity matrix, and apply the PCA transform on the identity matrix to extract the components. The way we visualize or present these components is very simple. All we need to do is create a new data frame, and then we create the components, we put in the components, and we have the columns as, let's say, PC1, and then PC2, PC3, as we have 4 of them, we just need 4. And then we need to say the index is our columns from the data frame. And here what you can see is we have successfully then took the components, and the components have represented how different features are weighted to explain the variance using the principal component. So for example, here the first principal component is composed of almost equal parts sepal length, petal length, and petal width, and maybe half of it and in a different direction the sepal width, whereas the second component is more majorly from the sepal length and a little bit from sepal length and not much of the other 2 variables. And by understanding this, you can then kind of see what are the important features and how they're contributing to your principal components, and that would allow you to make better decisions downstream as you feed this as a machine learning pipeline. And that's a wrap. So let's take a look at what we've just learned. So we've just learned how to apply the PCA algorithm on the iris datasets. We've learned how to understand the output of PCA and what it does. And we've learned how to extract the factors that contribute to each principal component. Or put another way, we have understood what are the weights that allow us to reconstruct the linear combination of features of the original datasets that allows us to then create the final principal components that came out of the PCA procedure.